Spring and block oscillator. Force constant and effective mass of a spring. Title: To find the force constant and mass of helical spring from the graphs of small m minus capital M against x and t square against capital M respectively, using method of oscillations. Introduction. According to Hooke's law of elasticity, within elastic limits, stress developed in a body is directly proportional to the strain produced in it. Thus, when an elastic body is deformed, a restoring force originates in the body to resist the deformation. If a body of mass m is attached to a spring of force constant k, whose other end is fixed to a rigid support, is displaced from its equilibrium position and released, performs SHM having a period given by t is equal to 2 pi into the square root of m upon k. Equation 1. In case of a vertical helical spring, the mass of the spring causes some elongation of the spring, and the center of mass of the spring oscillates along with the body attached to the spring. Hence, the time period of oscillation is given by t is equal to 2 pi into the square root of m plus m0 upon k. Equation 2, where m is the total mass actually attached to the spring and m0 is the effective mass of the spring in oscillatory motion. Theoretically, it can be shown that m0 is 1/3 the mass of the spring in the case of uniform helical spring. Squaring both sides of equation 2 gives t square is equal to 4 pi square upon k into brackets m plus m0. Equation 3. The graph of t square versus m is a straight line with an x-intercept equal to m0. Since for t square is equal to 0, minus m is equal to m0. Suppose a body of mass m is hung from a helical spring. The position of the pointer attached to the spring is considered as 0. Now, if m is replaced by a mass m, the displacement x of the pointer from the above 0 position will be proportional to m minus m, that is, small m minus capital M. A graph of m minus m into g against x shows how the restoring force varies with x. The slope of the graph is minus k. Apparatus. We require a jolly balance, weight box, a hanger with slotted weights of 50 gram and a stopwatch. A jolly balance consists of a vertical helical spring arranged in front of a calibrated scale. Procedure. Let us determine the mass of the spring m0. First of all, let us draw a table with columns observation number, mass added to hanger m2 in gram, total mass, that is capital M is equal to m1 plus m2 in grams. Time for 20 oscillations with 4 subcolumns, 3 for observations and 4th for mean t. Period t, that is capital T, is equal to t upon 20 in seconds and t square in second squares. Observation number 1, mass of the hanger m1 is equal to 50 gram. Suspend the hanger at the end of the helical spring. Place a mass of about, say, 50 gram in the hanger. Wait for some time for the hanger to be motionless. Observe the position of the pointer on the scale The tip of the pointer gives the equilibrium position of the oscillating system. Slowly pull the mass, that is the hanger, down and set the spring into small vertical oscillations. Oscillation should be counted as follows. When spring is displaced to extreme position, the spring goes to equilibrium position, then upper extreme will come back to equilibrium and again to lower extreme. This completes one oscillation. With the stopwatch, let us note the time T1 for 20 oscillations. It is found to be 12.8 seconds. Two more observations, T2 and T3, are taken. They are now T2 is equal to 12.6 seconds and T3 is equal to 12.7 seconds. Mean time T is equal to T1 plus T2 plus T3 upon 3 is equal to 12.8 plus 12.6 plus 12.7 upon 3 is equal to 12.7 seconds. Now find the periodic time T is equal to small t upon 20 is equal to 12.7 upon 20 is equal to 0.635 seconds and T square is equal to 0.4032 seconds square. Note in the table 1. Now put 50 gram more into the pan. Record time for 20 oscillations for 3 times and find mean T. Period T, that is capital T, T square in table 1. Take a series of 5 such measurements by increasing mass in the hanger by 50 gram each time. Now, plot a graph with T square along the y-axis and the corresponding m values along the x-axis. Draw a straight line passing through the plotted points. Extrapolate the straight line graph to meet the m-axis. The intercept on the m-axis gives m0, the effective mass of the spring in oscillatory motion. Procedure. Let us place a suitable mass m2 in the hanger so that the spring is stretched to 3 times its relaxed length. Note the total mass attached to the spring M is equal to 200 gram. When the hanger is motionless, note the pointer position on the scale x1. It is 67.5 centimeter. To record observations with different masses added to the hanger, we require an observation table with columns observation number, mass added to the hanger M2. Total mass attached to spring M is equal to M plus M2. Pointer position x2 centimeter. Extension of the spring x is equal to x2 minus x1 centimeter. M minus m in gram. M minus m into g in dyne. Now, add 50 gram to the hanger so that the total mass m is greater than m. Note the pointer position. Let us call this as x2. It is clear that x2 is greater than x1. The extension of the spring is x is equal to x2 minus x1. So, observation number 1, m2, 50 gram. M is equal to m plus m2 is equal to 250 gram. x2 is equal to 72.2 centimeter. X is equal to x2 minus x1 is equal to 72.2 minus 67.5 is equal to 4.7 centimeter. M minus m is equal to 250 minus 200 is equal to 50 gram. M minus m into g is equal to 50 into 980 is equal to 4.9 into 10 raised to 4 dyne. Take 2 more readings, each time adding 50 gram. Observe the corresponding extension and note all the readings in table 2. Now, we adjust the mass in the hanger so that the total mass m attached to the spring is less than m by 50 gram. Note the pointer position. The x2 is less than x1. Find the extension x is equal to x2 minus x1. This is negative. Enter the readings in table 2. Take 2 more readings and enter in table when the mass is reduced by 50 gram each time. The force constant K is the force per unit extension. It is given by the slope of the graph of m minus m into g versus x. Plot a graph of m minus m into g along the y-axis and x along the x-axis. Draw a straight line passing through the points. Find the slope of the line. It is slope is equal to BC upon AC is equal to y2 minus y1 upon x2 minus x1 is equal to 12.6 into 10 raised to 4 minus into bracket minus 12 into 10 raised to 4 upon minus 12 minus 11.6 is equal to 24.6 into 10 raised to 4 upon minus 23.6 is equal to minus 1.042 into 10 raised to 4. Hence, the force constant K is equal to minus slope is equal to 1.042 into 10 raised to 4 dynes per centimeter. Result 1. Mass of helical spring M is equal to 3 into effective mass M0 is equal to 3 into 25 is equal to 75 grams. 2. Force constant of the spring is equal to 1.042 into 10 to the power 4 dyne per centimeter. Precautions 1. While noting down the pointer position, keep your eyesight parallel to pointer. That is, remove the parallax. 2. Measure time for large number of oscillations so that error involved in the measurement of time will be less.